Hello everybody and welcome to the 13th lecture of MHM 42780 MUA 781. In the last session we talked about mass diffusion and we also showed that how similar it is to the heat conduction equation. So now we need to find comparable boundary conditions to determine the concentration distribution in a medium, because if you remember that the heat conduction equation, when we talked about conduction heat transfer, we started from Fourier, and after that we find the temperature distribution inside the solid. In this case we are going to do the same. So first we need to find the compatible boundary conditions, and then we solve the Fick's law or Fick's equation to be able to find the concentration distribution in a medium. If you remember from heat conduction, we had two common or very usual type of boundary condition. We had either a specified temperature boundary condition, we had a specified heat flux boundary condition, or we have insulated boundary. To be able to find concentration distribution, we need to find comparable definition for these three boundary conditions. Okay, so we need to know that despite the similarity between conduction heat transfer and mass diffusion, there is an important difference between temperature and concentration. Temperature is continuous while concentration is not. What does it mean, like temperature is continuous while concentration is not? For example, the wall and air temperatures at the wall surface are the same, but the concentrations of air on the two sides of a water or air interface are different. And you can see here, it's mentioned. You see? It's clearly mentioned here. Concentrations are different. One is on the down side of the boundary, the other one is on the top side of the boundary. So you need to be really careful and pay attention to these differences between concentration and heat. Okay, so now the question is how we are going to deal with it. In this case, specifying the location is not enough. We also need to specify the side of the boundary, because, for example, if I say that at let's say at x equal to 0, the y H2O is equal to what? I have two different numbers, so I need to specify the side. For example, liquid side, or I'm talking about gas side. Okay, so the location is not enough. We also need to specify the side of the boundary. To do so, we consider two imaginary surfaces on the two sides of the interface. As you can see here, two imaginary, very close to each other. Okay, in a way that there is no interference with the location. For both of the cases, the location is still y is equal to 0. Sorry, it's not x equal to 0. Y is equal to 0 because x is in this direction. Y equal to 0. So we have two imaginary surfaces on two sides of the interface, which is so close to the interface. Look at the picture, we can write it like that. So at x equal to 0, actually x equal to 0 and y equals to 0, so both of them can be, because it's like fine. At x equal to 0, H2O, liquid side is equal to Y1, and H2O gas side is equal to Y2. Liquid side here is 1, side is 0. Okay. How about a specified heat flux? Because if you remember, we said that we have three different boundary conditions. We have a specified temperature, we have a specified heat flux, we also have insulated. Okay. So how about the specified heat flux boundary condition? Okay, let's see. So for a specified boundary condition, let's use Fick's law. Let me just write it down here. You remember that? So this is the Fick's law. So if we want to have a specified heat flux boundary condition, let's say at x equal to 0 and diffusing a species of A, so easily we can say that for a specified diffusion flux, which is equal to a specified heat flux boundary condition, will be like this. See, dB dya is equal to 0. It is equal to a constant. Why? Because we say that it's specified, A and 0. Or we can also write it like this: dAB dWA dx at x equal to 0 is equal to AO. We call this one mass flux. We call this one mole flux. So basically two different ways of showing it. One is mass based and the other one is mole based. If you remember, what was Y? Mole fraction. What was W? Mass fraction. What is DAB? Binary diffusion coefficient or diffusion coefficient or mass diffusivity. What was the unit of DAB? 2 per second. Okay. How about insulated surfaces, because boundary condition? Because we talked about a specified temperature boundary condition, we talked about a specified heat flux boundary condition, and now it's time to speak about insulated boundary condition. As you can see, it's very similar to each other. So if we have insulated surface in terms of like heat transfer, the boundary condition will be this one: the temperature gradient on the surface, or let's say if x is equal to 0, at x is equal to 0 is equal to 0. So if we use the same mentality, we will have the same. So gradient of concentration at x equal to 0 is equal to 0 if the surface is impermeable. The same meaning of insulated, but there is another word because it means that no mass can be transferred from one side to another side. It's not about no heat can go from one side to another side. But in order to understand it a little bit better, let's solve two examples and see how we can get it right. So first is saying that the question is asking write three boundary conditions for mass transfer on a mass base, okay, mass base for species A at x equal to 0 that correspond to a specified temperature, a specified heat flux, and convection boundary condition in heat transfer. Okay, so for a specified temperature corresponds to a specified temperature, a specified temperature. So basically it will be a specified concentration, and is saying that how we are going to write it, mass base, not mole base. So is asking for mass base. So and x is equal to 0. The first one. The second one is saying that a specified heat flux. So a specified heat flux is equal to a specified mass flux. Why mass flux? Because we said that it should be mass flux. Otherwise, we could say if it was a mole flux. So if we want to apply that, rho dAB it's x equal to 0 is equal to AO, mass flux at A. And the third one is saying that convection boundary condition in heat transfer. Okay, what is convection boundary condition? So the corresponding to the heat convection will be mass convection. So then AS is equal to minus dAB WA x equal to 0 is equal to H mass minus WA and infinity. Okay, so we defined all those three boundary conditions. So please find the answer for 14.26 by yourself. Okay, now what we are going to do is let's talk about another concept that so basically now we know all the different forms of boundary condition, but the only problem is how to find the values. To apply a specified concentration boundary condition, we must know that the concentration of a species at the boundary, we should have it, because it said a specified concentration boundary condition here. So if we don't have this value, so basically we don't have the boundary condition. But how we can find those information? This information is usually obtained from the fact that thermodynamic equilibrium must exist at the interface of the two phases of a species. In this case, for example, let's say we are talking about air and water interface. The concentration values of water vapor in the air are easily determined from saturation data. Situation is more or less the same as solid liquid interface. Again, we use thermodynamic equilibrium for that. We know that at a given temperature only a certain amount of solid can be dissolved in a liquid, and the solubility of the solid in liquid is determined from thermodynamic equilibrium. So solubility, we can define it as the maximum amount of solid that can be dissolved in a liquid at a specified temperature. But how does it work? Let's say let's just like open another page and I start talk about it a little bit. Just like I want to give you one example. So for example, we talked about solubility. So solubility as for salt, solubility of salt in water at 310 for 100 kilogram of water is 36.5. Quite a lot. But why we mention temperature? Because we know that the temperature can affect solubility. So let's say we have it. How we are going to calculate the basically, let's say we want to calculate some kind of boundary condition in terms of like a specified concentration boundary condition. How we are going to do it? So in this example, or in this case, for example, the mass fraction of salt on the liquid side. If you remember, we said that those specified concentration boundary conditions, they have two sides. Okay, the liquid side, how we are going to calculate it basically is m salt, mass of salt, the total mass. Okay, what is the mass of salt? We said that for every 100 kilogram of water we have 36.5 kilogram of salt. So 36.5 kilogram of salt we have it. So 36.5 plus 100, 136.5 is 267. Okay, so easily we found the specific concentration of salt at liquid side. How about the liquid gas interface? Because we talked about air, water, we talked about now the solid liquid, but how about the liquid gas interfaces? For solid and for liquid and gas interface, we use a law called Henry's law. Henry's law. Henry suggested that there is like a correlation that yi and liquid side is equal to pi gas side divided by h. It's all at interface. How you are going to find this h? So h is Henry constant and is given in table 14.6 of your textbook. But can I use it everywhere, or so anytime that I'm dealing with liquid and gas interface, can I go and use the Henry's law? No. It's just like valid for dilute solutions, not for every single situation that you are facing with. Okay, so then what are we supposed to do if the solution is not dilute, like ammonia in water? In this case, we use another law. So let me just like open another page. Okay, let me just write it here for reference, that dilute solution. But if it is not dilute, he said that we are going to use another law, Rhodes law. Basically it's a correlation, and the correlation is as follows: pi gas side is equal to yi gas side multiplied by total pressure, and this one is equal to yi liquid side multiplied by pi sat. What is pi sat? Is the saturation pressure of the species I at the interface. Gases may also dissolve in solids. Like what? Like Coca-Cola that you drink, or lots of other things that we just like use or drink in our daily life. So gas may be also dissolved in solid. It is a very complicated phenomenon, and we are not going to discuss about it in detail. Just you know that we have reversible and irreversible gas solid dissolution. Reversible is like carbon dioxide in water, or like the soda that you drink. You can just like shake it, and after that the carbon dioxide is going to go out of the liquid. But irreversible is oxygen gas dissolved in titanium, which forms TiO2 on the surface. So there are some reversibles, but there are also some that they are not reversible. The concentration of gas, like let's say species I, in the solid at the interface is, we can say it's Ci and solid side, and it's proportional to the partial pressure of the species in the gas. Proportional to it. It's proportional to what? Pi gas side. and can be expressed as this. Like if we want to write it into one correlation, we can just write it as this one. Ci solid side is equal to Pi gas side. This is I. What's the unit? Kilomole meter. Okay, so what is this then? Let's say my handwriting is bad, but can we get any kind of like indication what is it? It's called UDA and is solubility basically. Solubility data for some gas solid combinations are given in table 14.7. Please go and look at them. You don't need again to memorize anything. You just need to know where those tables are, what information they are giving to you, and if you need them, you just go there and you read your numbers from those tables. The production of the product of solubility of a gas and the diffusion coefficient, basically multiplication of the gas in a solid, is called permeability. How we are going to show the permeability is, let me just like open another page and explain a little bit here. So we said that solubility UDA product, if we multiply it by diffusion coefficient will give us another constant that we call it permeability, which is measuring the ability of a gas to penetrate into a solid. Okay, so basically it's very important. We are going to use it a lot, but now let's we talked about a lot of different things that they might look like that they are completely different with each other and they don't have any kind of like a connection. But if we solve some examples, I think you will understand clearly how we can use these correlations to simplify or problems, or find or solve it and find the answer. Okay, the first example that we are going to solve is the question 32 of this chapter. Determine the mole fraction of carbon dioxide dissolved in water at the surface of water. The temperature is given 300 Kelvin. The mole fraction of carbon dioxide in air is given, and the local atmospheric pressure is given as well. Okay, so now we have like some information that we might require, but what's the first step? So do you agree with me that we can say that the air at the water surface will be saturated? Therefore, we can say that the partial pressure of water vapor in the air at the surface will simply be the saturation pressure of water at that temperature. Okay, so how we are going to find it? So let's start with assumptions. First, we can assume that both water vapor and carbon dioxide are ideal gases. Okay, surface of water, so we know that air at the water surface is saturated. We know this one as well. Okay, now when we know that the air at the water surface is saturated, we need to find the saturation pressure of the water at 300 Kelvin. So the P sat of water at 300 Kelvin, if we go to the table, we can find that answer to be 3.6 kilopascal. So now it's 9. Now I'm confused. I don't know what will be the next step. I know some information, I can understand it, but I don't know how to connect the dots. So basically, if you want to connect the dots, first we need to know that what the question is asking us. Determine the mole fraction. So it's asking us for why carbon dioxide. Am I right? So how I'm going to find that one? If you remember, we mentioned something as Henry's law. Okay, Henry's law. You see that there is a mole fraction. This is like a pi, and there is like a constant that we said that we call it Henry's constant. So let's use this correlation then. Don't get yourself confused. First start with what you need to find. So basically from Henry's law we have this one. Okay, how H can be found? It's no problem. You go to the table 14.6 of your textbook. At 300 Kelvin, this H will be 1710 bar. Okay, but in order to find or determine the mole fraction of carbon dioxide, we need to find the partial pressure of carbon dioxide. How we are going to find that one? You remember we just talked about it in previous session, that partial pressure of carbon dioxide is related to its mole fraction as well as P of air, like basically total pressure. So do we have the mole fraction of basically carbon dioxide in air? Yes, we have it. Fine. But again, I don't understand that here is like YCO2, here is again YCO2. they are the same. What we are asking is like asking to determine the mole fraction of carbon dioxide, but at the same time the mole fraction of carbon dioxide is given. I'm confused. That's the reason we mentioned here. You remember that we talked about this? So there are two. It's based on which side we are talking about, okay? So that don't get confused. I'm going to open another page because it's those kind of like mistakes that normally students do, so I'm trying to explain it to you, for you to avoid that. So what is asking? Determine the mole fraction of carbon dioxide dissolved in water and at the surface. So basically is asking us always write like this: at liquid side, what we have side of gas side, which is equal to 0.005. okay, so those are the differences. This one is what the question is asking us. We said that for liquid side, from Henry's law, we have liquid side is equal to partial carbon dioxide divided by H. So H we can go and read it from the table. Table 14.6. At what pressure? So first from the temperature, basically from the temperature, and table 14.6 we can find H to be equal as 1710, but the unit for H is bar. Okay, so now we have H. So if we have the partial pressure of carbon dioxide, we can find the mole fraction of carbon dioxide in liquid side or dissolved in water. Okay, so we mentioned that we said at the beginning that both carbon dioxide and water vapor can be considered as ideal gas. So because when it's an ideal gas, we mentioned last session that P, like a partial pressure, is equal to CO2 gas side multiplied by P total, which here is dry air. So this will be equal to 0.005 multiplied by 96.4 is equal to 0.8482 bar. But because we want to divide, we need to convert it to bar. Sorry, here is kilopascal. We need to divide, convert it into the bar, so it will be 0.0482 bar. This is the kilopascal. Okay. But where did we get this number? How did we get that number? So I'm trying to just like explain it now. I'm starting from the back, so I'm going backward to show you what was the right point to start. We assume that both air and vapor are ideal gases. We also assume that carbon dioxide also is ideal gas. But just let's for now just focus on air and vapor. So then the partial pressure and mole fraction of dry air in the air at the surface of the lake are, so P dry air is equal to P total minus P vapor. Alright? This one is this number, which is here is in kilopascal, but how we find that one? P is mentioned in a question. Let me go back and show it to you. The local atmospheric pressure is 100, so this is 100 kilopascal, and P, or pressure of vapor, of course it's the saturation pressure at 300 Kelvin. How we find that? From table A9, we know that this is equal to 3.6 kilopascal. So basically P dry air is equal to 100 minus 3.6 is equal to 96.4 kilopascal, the one that we used here to calculate this the partial pressure of carbon dioxide, and after that if we divide we have the final answer. So by CO2 on the liquid side will be equal to 0.00482 divided by 1710. Both of them units are bar, so it's 2.82 10 to the power of minus 6. So it's very important to that both units are the same. Sometimes a student use just like go to the table and read it and they forgot to mention that the unit was bar, and after that they put here kilopascal, they divide by, the answer is wrong. Why? Because when you want to divide two values to get a dimensionless value, those two numbers they should have the same units, otherwise you can't generate a dimensionless value like molar fraction or mass fraction. So basically what we did, it was first we assumed that carbon dioxide and water vapor are ideal gases. After that we said that okay, because it's ideal gases, we can say that the P of dry air is equal to the total pressure, which is 100 minus P of the vapor. But how we could find the pressure of the vapor? But by going to the table and reading the pressure, the saturation pressure at that specific temperature. We did that, we found the dry air pressure. After that we said that okay, it is we consider carbon dioxide as an ideal gas, then the P of carbon dioxide will be proportional to the mass molar fraction of carbon dioxide, but on the liquid side multiply by dry air No, it does not make sense. Why? Because we are speaking about the P dry air, so the molar fraction needs to be for the gas side. We had it from the question, so we put it, we find the P carbon dioxide or the partial pressure of carbon dioxide. By having all those values, we went and we said that okay, now we are going to use the Henry's law. We went to the table, we found Henry's constant. After that, we divide those two numbers here, and we found the molar fraction of carbon dioxide, but in liquid side, which in this question was dissolved in water. Okay, let's try and see if we can solve another one with the because it's like, I think when we solve more example, it will be much easier for us to understand. So here, another question, 34 of the textbook. Consider a glass of water in a room at 20 degrees and 97 kilopascal. Okay, so we have the basically T of environment and P atmospheric, 97 kilopascal. If the relative humidity, so we have relative humidity is equal to 100%, and the water and air are in thermal and phase equilibrium, determine A, the mole fraction of the water vapor in the air, and B, molar fraction of air in water. Sorry. So what is asking us is, first is asking for the mole fraction of water vapor secondly is asking for mole fraction of air liquid side. So again, liquid side, Henry's law. So if we have the P of basically dry air, we just mentioned dry air, the gas side divided by constant that we read from the table, we will find this one. But how about the mole fraction of water vapor in the air? If you remember, it's, and like previously we mentioned it, just like 1 or 2 minutes ago I mentioned it as well when we were busy solving the previous example. So in this case we know that this one will be P vapor divided by P total. Okay, so do we have P total? Yes, we have it. What we need to find is just like the partial pressure of vapor. How we can find it? It's basically, we can go to the table, because we know that the pressure of vapor is equal to saturation pressure at 20 degrees, which will be equal to 2.339 kilopascal if we read it from the table. So then we have 97. So we easily calculated the first part of the question, the mole fraction of water vapor in air. If we follow the same strategy as the previous question, we can say that again the pressure of dry air is equal to P minus P vapor. Why? So it's obvious, because we said that that can be the case. So pressure of dry air is equal to 97 minus 2.339. This will be 94.66 kilopascal. So now we have this one. We go and read the H from the table, and we can find the mole fraction of air in the water. But we need to think about that H. When we read it from the table, the unit is Pascal, but here we were speaking, the unit is bar, while the pressure of dry air on the gas side we calculated based on the kilopascal, so we need to convert it. Okay, if we do the calculation, the final answer for Y of dry air liquid side will be equal to 1.44 10 to the power of minus 5. Okay, so that's it. I think that's enough for today. If you didn't understand like a part of the concept, or don't worry, please go through your textbook, read your textbook, watch the video one more time, and I'm sure that you will understand it. If there is any problem, of course, always you can ask. Enjoy the rest of your day. Bye bye.